So the session is, of course, if you have not already seen, it's about MPLS VPN, specifically deploying MPLS VPN. I'm not going to try to talk about what MPLS is and what TE is and ATOM. I'm going to focus more on the MPLS VPN. We'll rush through the basic stuff about MPLS VPNs, but not going to get a lot of details into like how VPN works per se. I'm hoping you guys have already gone through that and played with VPNs and whatnot. So how many of you have actually deployed, configured, or played with MPLS VPN? For how many of you it's fairly a new topic? Okay, so I apologize, I'm not going to spend a lot of time about the basic stuff, but I'll focus first few minutes of my presentation talking about the basics, how it works, and few elements. But I want to really focus more on the services. I think that's one of the important topics. A lot of folks who have deployed and played with it, it's more relevant now. And I would strongly encourage, if you have not really gone through what the basics are, attend either Introduction to MPLS or maybe attend one of the tutorials. Okay, so again, my name is Rajiv Asari. I'm a technical leader at Cisco. I work out of RTP. I've worked with more than, I would say, 100 providers and enterprises around the world just doing MPLS stuff. So do a lot of consulting work, I do a lot of now standardization work as well. I just got my first IETF draft submitted, and 2 more on the way, etc. A lot of design and deployment, but almost no development within Cisco that I get involved in. So I don't do any coding, but I have fairly good understanding of what's out there in the code and whatnot. How many of you are from the service provider side? And how many of you are from the enterprise? Wow, so really good mix from the enterprise side as well. Anybody from the government specifically, per se? Okay. So the agenda is fairly simple as it looks on the slide, but it will get pretty detailed. So we're going to focus a little bit about basics in the first bullet item, just explaining what MPLS VPN is. We'll then spend most of our time into the services side. What services can we offer using MPLS VPN? Then we'll touch upon a few of the advanced topics, and it's really relative. I don't know if I want to call it advanced, but enter ASVPN and carrier supporting carrier is what we're going to talk about in that advanced section. And then a couple of minutes I'm going to focus on best practices, something that you guys really take back to your workplace and apply to your network, etc. And then just conclusion. So definitely you guys are all gung-ho about MPLS VPN as much as I am. Hopefully you all understand the IP routing concept, specifically BGP, because BGP is the key in MPLS VPN, as you would all know. I'm not going to talk about any basics, MPLS position, disposition, and whatnot, assuming you guys have all gone through that. And ask me questions. Make it interactive. I try not to limit questions that get asked, but given that I have only 2 hours, I'll do my best. And ask me any question that pops up in your mind. And I don't have the concept of stupid question, so don't just hold on to it. But of course, I do have concept of good and bad questions, right? So, but I say ask me bad questions because I categorize bad questions as the ones that I don't have good answers for. Bunch of terms, you guys, all of you have the handouts, so I'm not going to go through all these terms, but these terms are something you have to familiarize yourself with, given that these terms are commonly used in MPLS paradigm. So let's quickly run through the control plane and the forwarding plane section of just understanding how MPLS VPN works. Right? So within the MPLS VPN paradigm, or within an MPLS network, you have the PE routers and P routers. P routers are the ones that typically sit at the edge, okay? And they definitely speak some sort of MPLS with other routers within the MPLS network. However, they speak same old IP with the customer edge routers. P routers, on the other hand, they have no awareness of VPNs. They are the core routers. They don't need to run even BGP for that matter, but they must run something that can enable them to understand what MPLS packets are, right? So ability to look at the MPLS packets and forward those MPLS packets by building the relevant label information base, or LFIB. And of course, the same old stuff, it has to have an IGP to know about all the internal routes, and most importantly, the next hop routes, right? So in MPLS VPN, you would hear this many and many times that next hop is such an important field, and it is so because the LSP, or the label switch path that gets built from an ingress router to egress router, is based upon that next hop field. So when you advertise a BGP route, the next hop attribute of that route is what the ingress router is going to build the LSP to. So as long as there's a specific route to that next hop within the IGP, and as long as there's a label for that next hop prefix within my MPLS domain, the LSP will just work fine. It will get established. So we'll focus more on that later in the presentation as well. One thing that MPLS VPN does bring to the table, and it's very important to understand, that there's a concept of virtualized routing table. So those of you who have not heard of MPLS VPN before, if you have, you might as well know that there's a global routing table. If I just to show IP route, I'm looking at global routing table. In addition to that, now we have multiple virtual routing tables. So we call them VRF routing table, virtual routing and forwarding instance. One VRF routing table doesn't talk to another VRF routing table, and that's why we call them virtual, right? So just think of it, I got multiple virtual routers sitting within the router itself. Although the analogy is crude because there's clear differences between virtual routers and logical routers in VRF. But just for the high level understanding, think of it that way. With each of these VRF routing table, we also have the VRF forwarding table, the CEF table, which get used to forward the IP packets. So all the routes that PE would receive from that specific CE router or from another PE router belonging to that VPN, all those routes will get stored in the relevant VRF routing table. So if you have blue, it goes into the blue. If it is a green VRF routing table, the routes get into the green VRF routing table. And all the routes that are within the IGP or the BGP inside this MPLS backbone, they go into the global routing table, right? Same old stuff. So what's a VRF? It's virtual routing forwarding instance. Basically it creates this virtual routing instance within the router. Then we can associate a given customer edge router to this VRF instance, right? So we define a VRF by configuring a route distinguisher, the relevant route target parameters, and the name of the VRF itself. So you will hear a lot of people saying VRF, other folks saying VRF, one and the same thing, just different terms. All the routing protocols now are VRF aware. So whether you like to run EIGRP or ISIS or OSPF or RIP for that matter, or even static, everything is VRF aware. So could run any kind of routing protocol between PE and CE, and each of those routing protocols would have its own instance within the VRF address family. We'll see that later more in detail. CE router runs standard software. So whatever the CE router is doing doesn't have to be Cisco, could be any router. As long as that CE router can speak IP routing, that's all it needs. Of course, PE router has to have this specific RFC 2547 support, which provides MPLS VPN functionality. So all the routes that are advertised by the CE router towards the PE router would install those routes in the relevant VRF routing table. Anything that comes from the global interface, be that IGP or BGP, those routes get installed in the global routing table at the PE router, right? And those global routes by default do not get advertised towards any of the customer edge routers that are within the VRF. If you are familiar with how BGP update looks like, BGP updates typically are organized based on the common BGP attributes. For MPLS VPN, there's a new attribute called MP_reach_NLRI. Previously, for just plain IP, it was just NLRI attribute. Within the MP_reach NLRI attribute, we encode the VPN v4 address based upon the common route targets along with the label. So let's look at what this VPN v4 address really is. It is an IPv4 address really combined with a route distinguisher. Route distinguisher is something that is an 8-byte entity. It's not an attribute, so don't get confused. Route distinguisher is not a BGP attribute. Route target is. So route distinguisher really a numerical entity that gets appended to the same old IPv4 address. So 8 plus 4, 12 bytes. So the VPN v4 address is a 12 byte long entity. The purpose of route distinguisher really is to make the IPv4 unique within the provider address. Why? Because there might be more than one customer using the same 10/8 address space. In other words, VPN customer may have overlapping address space. So if there are overlapping addresses, the provider within its network must make them unique somehow, and RD is what that provides us the ability. The VRF gets configured as shown on the right bottom side of the screen. You just put IPVRF, the name of the VRF, and you have to put the route distinguisher. If you do not put route distinguisher, the VRF is not really defined. Router would not accept or would reject the config itself. Route target. Route target is a BGP attribute. It's also an 8-byte field, and it simply is a way to color the VPN v4 prefix. And a crude analogy I like to give, if three of you are from one company and 3 of you are from another company, right? You get classified when you register at Networkers. You are from this company or that company, and then so that would be an RD that you got classified, and so 3 of you are distinguished from other 3, and then each of you can choose one or more sessions that may or may not have the commonalities. So that's something like route target. So route target defines which VPN route gets accepted by which PE router and goes to which VPN. And then the label. Label is something that's carried within this MP reach and LRI attribute itself along with the VPN v4 prefix, and it's usually assigned by the PE router that changed the next hop or that declared itself as the next hop address for that VPN v4 prefix. So along that same line, if any PE router changes the next hop information of that BGP attribute of that VPN v4 prefix, by law of BGP, that router must assign a new label to that VPN v4 prefix and advertise it to rest of the network. And this point, as simple as it may sound, is very important when you're doing inter-AS VPN. PE addresses, right, the next hop addresses, usually we put those addresses like by using router ID or by using specific next hop statement and try that to loop back 0 interfaces. One of the common practices. When we are doing MPLS VPN or MPLS in general, make sure you do not summarize those PE loopback addresses in the MPLS backbone. So no matter what you learn from any other session, doing all the routing stuff, that summarization was good, and I'm saying it's not so good when you enter the MPLS paradigm. If you do summarize the PE loopback addresses that are used as the next hop addresses by every other router to build the LSP to, if those specific routes are gone, then we lost the ability to build specific LSPs, and MPLS forwarding will not work. Question?
Yeah, I'm curious where
the question is, in the previous slide I had MP reach and LRI attribute. Where is the subnet information? And by the way, just to answer that question, this has nothing to do with MPLS VPN. This is more of a BGP 101 question, and I'll answer it too. There's no subnet masking encoded within the NLRI attribute. The way subnet masking gets calculated is by looking at the number of bits that BGP has used within the address. So if it's /30 or if it's /24, the last octet is not used by BGP at all because /24. If it's /16, the 2 bytes are gone. So the BGP would only encode the first 2 bytes of an address of a prefix if it's /16. So that's how the receiving router would implicitly know, oh, so it's /16 subnet. And that's how you would see when you do show IP BGP or iOS or any other router for that matter would calculate the subnet information. The same thing as in VPN. So having learned all that, right, let's put it together and see how does the VPN control plane works from end to end, from CE1 on your left-hand side to CE2 on your right-hand side. CE1 would send a prefix advertisement using whatever routing protocol to the PE router. PE1 would translate that received IPv4 prefix into a VPN v4 prefix. And by saying that, there are 3 steps that get involved in the process. 1, it assigns a route target according to the VRF configuration, and VRF is tied to this interface, by the way. It rewrites the next hop attribute to itself. So within the BGP, we'll see in the next slide that PE1's address, typically the loopback 0 address, as you would have configured within BGP configuration would show up in that next hop information. And then of course, because it changed itself to be the next hop of that VPN v4 route, it must allocate a label. So it allocates this label, also sometimes known as local label or incoming label from the MPLS perspective, for that prefix, and it provides that information within the BGP update itself. And then it would send this, it would construct the multi-protocol BGP update message and send it either the route reflector or all other MPI BGP neighbors, PE routers, if there's no route reflector and there's a full mesh. So notice here, within the MPI BGP update, you have the VPN v4 prefix, which is, some RD value, colon, what are the prefix the site one had, 10110, the next hop being PE1, there's a route target that's configured within the VRF at PE1 for this interface, and the allocated label value. All this information is advertised to PE2, and when PE2 receives this prefix, right, it's going to do a check. Am I supposed to, or am I allowed by the mean of configuration to accept this update message? So what it's going to do is PE2 is going to check if the route target green is configured as the import route target within any of the VRF locally configured at PE2. And route target would look something like this, a number colon, another number. And if it is configured to accept, PE2 will install that information within BGP, and it will translate that information back into IPv4. At that point, it will select the best path, install the best path into the VRF routing table. Of course, as soon as that happens, the CEF table also gets updated with that prefix, and at last it will advertise that prefix back to CE2 as an IPv4 prefix via what our routing protocol may be configured. Note that the routing protocol used on the left-hand side at PE1 CE1 doesn't have to be the same as the one used on PE2 CE2. It could be anything. Question, sir?
Is the label aggregated?
So the question is, the label that gets allocated by the PE router for a VPN prefix, is it an aggregate label to cover all the prefixes advertised by the CE router, meaning there's only one label to designate all the prefixes advertised by CE router? The answer is not today. What Cisco IOS does is by default it allocates one label or a label unique to a prefix. So if there are 100 prefixes behind the CE, we'll have 100 labels. In the forthcoming release in 1240 and 12.230S, I believe, we are going to have per CE label knob as well. So if you really desire to include per CE label or per VRF label for that matter, you could configure PE to do so. So you will have the ability in very short time. Question, sir? Okay, so the question is, well, when PE2 receives that BGP update with the green route target, and if there is no green route target configured as the import route target at PE2, what does it do? Well, it basically discards that BGP update altogether. Those prefixes are not stored. You will not see them at PE2. And it makes sense, right? So the point here is that if there is no VPN customer that's interested in the green VPN routing information behind PE2, why should PE2 bother keeping that information? Why waste my memory and precious resources for something that's not needed? That's why we just discard them. So the question is, why even bother sending it? Well, so think about it. This is a full mesh network from the perspective there are hundreds of PE routers. There may be a couple of route reflectors. How will PE2 know whether I send this prefix to this PE but not to that PE? And if it could figure it out, and by the way, there's a proposal at IETF to do that called RT constraint. And I always oppose that idea for the simple fact that if I as a router have to build dedicated BGP update message to each and every router, because this PE router needs 200 prefixes, but this router needs only 100 prefixes. But guess what? I just lost my efficient ability of formatting my BGP update once and replicating it twice. I just lost that whole ability. So it impacts convergence. Not many people realize that. They think, well, it's very good. I can send what is relevant to the egress router, but it completely breaks the replication model of efficiency at the ingress router. So I'll be really surprised if that feature ever takes off, but that's just me. So we understood the control plane. So let's try to put together what happens in the forwarding plane in an end-to-end flow basis. Just like for the route that got advertised from CE1 to CE2, we'll travel back and say when the CE2 has to send the packet back to CE1, for that prefix, where does the imposition take place and whatnot. So before that, let's understand the concept of where the routing table is, where's the CEF table and whatnot. So the CE1 had advertised the prefix to PE1, which was a VPN prefix, and it got to PE2 and no other router, and so on and so forth. In parallel, PE1 and PE2, in conjunction with all these core routers, might have built their global routing table and global CEF table to store the information regarding how do I get to PE1 or how do I get to PE2, right? So there would be the destination being PE2. To get to PE2, PE1 is saying my next hop is PE1, and the label to be used is 50. And this label information might have already been learned using something like LDP or RSVP or any other label distribution protocol. Okay, so that's your global forwarding table. Usually visible by just doing show IPsef, right, without any VRF extension. And then we have the VRF specific forwarding table that you would usually see it by doing show IPsef, VRF, blah, and the prefix. Point to note here is that the label information within the VRF is obtained by using BGP, right? BGP used to distribute the label information for VPN-v4 prefixes, whereas for global prefixes that are within the MPLS VPN backbone, we commonly use a mechanism such as LDP, but we could also use RSVP or, for that matter, BGP plus label. So let's follow what happens when CE2 now sends the traffic or packet destined to CE1 on your left-hand side to 10.1.1.1, for which CE2 learned the route via PE2. That point PE2 does a lookup in the VRF forwarding table, and it imposes two labels. Why two labels? Anybody? Thank you. So one label, the outermost label, is for the next hop. In this case, the next hop would be PE1. So the topmost label to get to PE1 and the bottommost label to get to the VPN prefix itself. So this is something, you could almost assume that in MPLS VPN, if the PE routers are not directly connected to each other, the VPN packet will always have at least two labels. When we are doing MPLS VPN, an MPLS packet will always have at least two labels if those PE routers are not directly connected. If they are directly connected, then there will be only one label because there will not be any label to get to the next hop. Question? The question is, does NetFlow export any of this label information? Yes, now that we have NetFlow V9, we can easily create the template and define whatever field we want to include and collect the information. Now, that doesn't mean it's available on the platforms right away. So that may be something you want to double check on which platform you're looking at. The question is, from PE1 to PE2, if there's an IP path and there's another MPLS path, which one will it choose? In iOS implementation, if the outgoing packet is an MPLS packet, and if there are two paths, it will choose MPLS path only. However, if the outgoing packet is just a simple IP packet, then it will try to load balance between IP and MPLS. So here, as it's illustrated on the slide, the packet going to 10.1.1 on your left-hand side gets encapsulated with two different labels, the topmost label being 25 and the inner label being 100. The label 25 gets swapped at the next P router, so label swapping, until the packet reaches the egress PE router. And by that point, the topmost label probably has been already popped, right? I'm sure you guys all remember the pop operation, the PHP, penultimate hop popping. Right? So when the packet gets to PE1, it only has one label to look up to, which is the label that corresponds to this specific prefix. Hence, the PE1 would convert that packet back into an IP packet, meaning it will remove the label stack from that packet and send the IP packet towards the CE1 router on that PE1-C1 interface. And this requires, of course, an MPLS lookup at PE1 for the label 100. So that's how it works. Any other question that for just the basic stuff? I know I kind of rushed through it. I'm not going to go through the configuration slide. I included them just for your fun. So you guys can look at it at your own leisure time. This is how you define VRF. This is the config you would need on the PE to P link from MPLS perspective. This is the config, and by the way, the router ID is rightly shown there. So this config is applicable to PE1, not to every other router, just to clarify the point. Then what configuration we need from multi-protocol BGP perspective, what configuration we need at the route reflector from multi-protocol BGP perspective, what config you might need on the PECE if eBGP was the chosen protocol. That's how we would configure it. If OSPF was the chosen PECE protocol between the provider edge and the customer edge router, then this is the relevant config. Note that OSPF is the only exception we have, and I pretty much dislike it as much as you do, that we don't have that same address family concept in case of OSPF, right? For EIGRP, for RIP, for BGP, we all do the address family kind of thing as it's shown on the top box. For OSPF, we follow what it used to be previously. You put router, OSPF, then the process ID, and then you associate that process ID with the VRF name. So OSPF is the only exception in this case. The question is, will there be any performance problem if I use multiple OSPF processes? Right? So early on, and I would say this is like two years ago, we did not have an ability to create multiple instances of a same OSPF process. So what would happen that we were always limited by the number of PDBs, the protocol descriptor blocks within iOS, and the maximum PDBs we could do were 32. So for every routing protocol, or for every protocol, we burned one PDB. With BGP and with EIGRP or with RIP, we actually burnt one PDB, but we had multiple instances within the PDB. So we never burnt more than one PDB, irrespective of how many customer or VRF BGP sessions or RIP sessions we had. With OSPF, 2 years ago, we didn't have that flexibility. So we're always limited by, say, we would have heard from your, either CCO docs or other folks saying that you cannot do more than 28 processes on a given PE router, meaning you cannot connect more than 28 CE routers within that VRF or across the VRF. So at the most 28, that's it. So 2 years ago, that restriction got lifted. Now we do the same thing as we did for BGP within OSPF. We only burn one PDB and follow multiple instances. So that's been something about scalability. For performance, there has been some work done, and we concluded that around, depending upon the platform, of course, 100 to 200 OSPF sessions were easily achieved without impacting the router performance from the memory perspective or the CPU perspectives. But that's very platform-specific question answer, by the way. Here's the RIP-specific config, then the EIGRP-specific config, and by the way, again, this is all relevant to the PECE side, right? So towards the customer. Then you can, of course, do static. How many of you offer actually static on the PEC, those who are from the provider side, right? And what's the biggest chunk of routing protocol distribution? Rough number. Is BGP the maximum number of, or static is the maximum? Yeah? Well, the comment here is the static is the maximum because it's cheap. It's a relative, of course. But that's somewhat true. I mean, US, I know for sure, static at one point was more like, 60%, and other routing protocols were like 40%. But that has changed, at least in US for sure, I know. It has kind of, the pendulum has shifted to the other side as more and more VPN customers are demanding dynamic routing protocol usage. So we're going to talk about these 10 services. Actually 11, there's another one coming. I didn't get a chance to modify the slide. And I'm sure some of you will find these services quite relevant to your network, either today or in future. Let's talk about load sharing. I know that's one of the most talked about topic, that hey, how do I provide load sharing in MPLS VPN network? And this load sharing is not something that is pertaining to multiple paths within the MPLS VPN backbone. This load sharing is more relevant to the VPN customer being multi-homed to the provider network and demanding load sharing on the PECE links or those multi-homed links, right? So something like this, in which the site A on the left-hand side of the screen is multi-homed to the MPLS backbone via this PE11 and PE12. So one model, of course, that the VPN customers would go for this is to get redundancy. Like, hey, if this PE11 and CE1 circuit fails, I want the traffic to come on PE12 CE1 interface. So I have redundancy. But now the model is more towards using load sharing. The customer would say, hey, I'm paying for 2 circuits. assuming they are. I've been told that there are cases in which provider actually offered the second circuit for free. It's like, hey, as long as you don't use this circuit, unless the previous one fails, I'm not going to charge you. Which makes sense, but as if I'm going to tell you. So this is the case. So that redundancy model is rather easier to achieve within MPLS VPN. However, if the requirement is to have the traffic coming from the remote site be load shared, okay, not load balanced, there's a difference. Okay, load sharing is the proper word in majority of the context, I would say, in Cisco IOS implementation. So if the requirement is to have this remote traffic coming on both of these circuits, it becomes kind of difficult to do so in the classic MPLS VPN case. So before I jump into that, I just want to expand the topology to make the point that, well, the multi-homing could be done either using 1 CE to 2 PE connections or 2 CE to 2 PE connections. But the mechanism by which we achieve the load sharing is the same, independent of the topology, right? So how do we do load sharing? So first thing we want to do is configure unique RD per VRF per PE for multi-home customer sites or interfaces. Okay, unique RD per VRF per PE. What that means? That means you would, if this site is multi-home, then the interface CE1P11 would get RD 300:11, and now this 300:11 cannot be used to designate any other interface belonging to that multi-home site. That's why, so now CE1P12 interface gets into the VRF green with a different route distinguisher. Okay. Along the same line, what goes on in the other VPN sites, the RD could be the same, could be different, depends upon your own flexibility. So one question that often comes, right? Well, hold on. So does it mean I have to keep track of each VPN customer site if it's multi-home, it's not multi-home? Geez, that sounds like a lot of work. I don't even have a provisioning system. Well, I'm sure you do, but. So the point here is that if you really want to be accommodative of your future growth, you could choose the model and make it the common model for all the VPN interfaces. Just put unique RD per VRF per PE for everything, for any VRF connection that you have. So in fact, ISC, the Cisco Provisioning Solution Center, right, for MPLS VPN, and you can see big smile when I'm saying that, does the unique RD per VRF per PE by default. So it saves you some pain from migrating a given VPN customer later on if they decide to go for this multi-homing. Because if you didn't do that originally, what's going to happen? Well, 6 months down the line, this customer site would say, hey, I want to do multi-homing to another PE router, and that means you will have to change the VRF configuration. That means there will be an outage. The way you would change the RD on Cisco router today is by removing the VRF and putting it back, because as we learned early in the presentation, RD is what that defines the VRF. If we have to change the RD, we have to delete and re-add that VRF with the new RD value. That means as soon as you delete the VRF, all the interface association with that VRF will be gone. So you have to put them back. Question, sir? So the question is, could I not do the load sharing within VPN by playing with any of the BGP attributes such as MAD on one of the sites instead of having to configure these unique RD per VRF per PE model? Okay, so the problem here is that if you just have to play with BGP attribute, that's not going to solve our problem really to get the load sharing, and I'll tell you why on the next slide. The final thing that would be needed to have load sharing configured is to use BGP multipath. Just by tweaking the BGP attributes for a given prefix, it's not going to help me anything, because to do load sharing on these links, this router must be configured such that it has both paths, one via PE11, the other via PE12. If I just tweaked any of the BGP attribute, then I can only choose one or the other path, not both paths, and that's what we're trying to solve here, right? So the question is, as soon as I enable multipath, will that increase memory consumption too? Of course. As soon as you have multiple paths for a given prefix, you will increase the memory consumption. The question is, do I have to assume that PE2 would have the same IGP cost to get to PE11 and PE12 to do BGP multipathing? If you just do eBGP multipath, that is one of the requirements, and that's why I don't recommend using simple iBGP multipath. I recommend using eIBGP multipath to get away from that limitation, because let's face it, in reality, it's very difficult to achieve that your PE2 will be equidistant to PE11 and PE12. That's not realistic to assume. And if you just put IBHP multipath, I'm sure some of you would remember the IBHP multipath rule of thumb is there should be both all the next hop advertising that path must be equidistant from the router, which is enabled with the multipath. So we don't want to have that limitation. Yes, sir. The question is, hold on, just because we proposed on the previous slide that PE11 would use a unique RD and which would be different from what PE12 is using, this prefix 171.68 will be uniquely known at RR via 300:11 171 blah 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 blah, and the other one 300:12 171.68 right? So they are uniquely known. Because they are uniquely known, route reflector will treat them as unique prefixes. That means route reflector will run their own best path algorithm for individually for each of those two prefixes and advertise both of the best path to all the remote routers such as PE2. However, what is going to happen when those two paths get to PE2? Both of them will get imported into which VRF? The VRF configured within the PE2 CE2 interface. Once they get imported into that VRF, how many paths for 171 are we going to end up at PE2? Because BGP 101 says when you do your best path calculation, you choose only one best path. That means routing table and the forwarding table will get only one best path. And do we want that? No. We want multiple paths because we want to have the traffic being load shared via both PE11 and PE12 egress points. That's why we need multipath at PE2. So we already discussed this path. Without unique RD per VRF per PE, RR would choose one best path right here. If we did not use unique RD per VRF per PE, RR would choose only one best path for 171.68 and PE2 would only get one best path. No multi-homing, no load sharing, nothing will happen. That's why we need unique RD per VRF per PE model for this. And yes, there is a memory consumption. Yes, sir. Question is, where does the EIBGP multipath get configured? Within the global BGP or within the VRF address family? It's right here. Within the address family IPv4 VRF green. Oh, the question is, how many paths can I have here? Is there any limitation from the CLI? Yes, indeed. We limit that to, I believe it's 8. It used to be 6, but we have it to 8. Or depending upon the platform, this might even be 16. Why 16 is the maximum number? Because we have only 16 hash buckets for the load sharing. Those of you who have dealt with Ceph before in your previous experience, or if you have not, then if you just do show IP Ceph internal for a prefix, you will see the list of hash buckets. It's all out there. And that's why we can only do 16. But this depends upon the platform and the hardware that you have at the line card. Because this is really an ASIC level function on a distributed platform. Yeah, we already discussed this. The EIBGP multipath implicitly provides both eBGP multipath and iBGP multipath for VPN v4 routes. Okay, let's talk about hub and spoke. So traditionally, right, hub and spoke model is used to limit VPNs or spokes not talking to each other directly. And MPLS VPN by virtue provides any-to-any VPNs. So if you have a customer or if you have a requirement by which you need to offer hub and spoke functionality to a given VPN customer, don't assume that because RFC 2547 or this MPLS VPN provides any-to-any, we cannot do hub and spoke. It's very much possible and fairly easy to implement hub and spoke VPN using MPLS VPN. And the whole magic lies in this import and export route target manipulation. Yes, sir. So the question is, well, how does load sharing work on this router such that some of the traffic will go on PE11 CE1 link and some of the traffic will go via PE12 to CE1 link? Will it be 50-50? Will it be 85-15? Will it be 40-60? Did I rephrase the question right? Okay, so let's see how many of you are well familiar with iOS load sharing concept. Is it going to be 50-50? Thank you. How does iOS load sharing work based on? Thank you. So what that means is if there is only one flow, let's assume the worst case. If there's only one flow originating from this side, going to this site A on your left-hand side, will the second link ever get utilized? Never. So the answer to your question is really depends upon number of flows and more importantly how those addresses are spread. Because at the end of the day it's a hash bucket calculation. What PE2 router would do in the Ceph when it receives an IP packet, it looks at source and destination as you said per flow, use that information, feed that into a processing logic. The output of that logic is one number from 0 to 15 and that number points to one of the hash buckets. And that hash bucket contains the outgoing interface information and the label stack. Question is, what happens if we do per packet load sharing at PE2? Yes, in that case, it literally is going to do per packet based load sharing. So for the same flow, you have one packet going this way, one packet going that way. And I'm sure some of you will say per packet is bad, right? For obvious reasons. So, but that has nothing to do with MPLS VPN. So how do we implement hub and spoke? What you're trying to provide here is that all these VPN sites on your left-hand side of the screen, spoke A and spoke B, should send the traffic to each other always via the hub site. So traffic should always traverse the hub site first before going to any other place. To configure that, there's a little tweak in any-to-any VPNs, right? Like the one we discussed before. Route target import was always the same as route target export. That is what that defines any-to-any. Everybody gets everybody's routes and everybody can reach everybody else. And hub and spoke, we don't want that. Meaning they're really not part of the same VPN. It's not really any-to-any. So what is mandatory here, and remember that, what is mandatory to implement hub and spoke is to choose unique RD for every spoke site because we don't want them to talk to each other directly. Also, make sure that the export route target is never equals to the import route target within the VRF, right? So here the export is 1:1, import is 2:2, and the same route target policy is configured on every other PE router's VRF that connects to the spoke sites, right? So same export 1:1 here as well as here, same import 2:2 here versus here. RD is always unique. That's mandatory for hub and spoke implementation. On the PE router that connects to the hub site, we would use two VRFs and two interfaces. These interfaces could be either logical interfaces as shown on the slide, or they could very well be two separate physical interfaces. Now notice that one VRF on the hub site, we call it hub out, just to make it more meaningful, that this VRF will be used to receive the traffic from the hub towards the spoke. And this VRF will only import and nothing else. In the contrary, we have another VRF configured on the same PE router connecting to the hub site, which will have only the export statement. So hub out will be placed on this red link and hub in will be placed on the blue link. Okay, both of those interfaces connect to the hub site. In addition, if you do have BGP as the PE-CE routing protocol between your spoke sites and the PE routers and the PE hub and the hub CE, then it's mandatory that you use these knobs called AS override and allow AS in. How many of you are familiar with these knobs? Should I explain that? Okay. What this AS override does is that so assume that you had AS number 200 being used in the spoke site A and the same AS number 200 on the hub site as well, right? And that's fairly common practice for your VPN customers to have the same AS number independent of how many sites they may have. When that happens, BGP 101 says what? That if the BGP update received by a router contains its own AS number, then that router should do what? Discard it. That means anything coming from this spoke, any routes being advertised by the spoke router will never get accepted by the hub router. This AS overrides knob actually overrides the customer AS number with the provider AS number so that the AS path becomes unique when it hits the hub CE router and gets accepted. Okay, so the route went from spoke A to PE spoke A. PE spoke A advertised that information via BGP to PE hub. PE hub advertised that to CE router on the hub side. Now the CE router advertises that information back. Okay, it doesn't have to, but we are making the worst case here, and that's what we are considering. Why? Because spoke A routes should be made available at spoke B, and to do that, hub should advertise those routes back towards the spoke side. So what happened when the prefix 171 got received at the hub CE? The AS path was nothing but the provider AS numbers. Then CE router advertises that back to the provider edge router. Well, now again, what's going to happen? Provider edge router would detect its own AS number in the AS path and would freak out and would just drop it. So we need to solve that problem too. So what we say, well, don't override, just allow AS. Allow my own AS. Now here you can limit number of occurrences of the AS number by saying I will only accept this AS path if my AS number shows not more than twice, or you can make it 1. So this is to avoid looping, right? Because if we keep mucking up with AS path, we may end up in some kind of looping scenario. Well, that's why the whole AS path was designed for, other than just tracking who is originating and where it's traversing. So you can put this number there to limit number of AS numbers occurrences. Well, everything is dangerous and everything is not dangerous. So the question is, hey, is there any other way I could provide this hub and spoke functionality without really changing or overriding or allowing my own AS to appear in the AS path because it's dangerous? The answer is yes, use different routing protocol. Okay, if you don't want to use different routing protocol, then understand what it requires to change the AS path. I would argue that it's not dangerous because you're only changing it for one VPN customer. Note that that CLI does not change the BGP processing in terms of AS path for any other VPN customer or for any other BGP neighbor than that within that VRF. So one thing in the red that I have flagged here is if the spoke sites only need the default route from the hub site. So what we discussed the last time, why would you need allow AS in? And I said that if the specific route, the more specific routes need to be advertised back to each and every spoke. Well, and some of you could say, well, who wants to do that? I would rather advertise an aggregate route, a summary route from the hub site to all other spoke. And that summary should contain everything. So that's one way to solve it, by the way, to answer your question. So you don't have to worry about allow AS in. If you can force your VPN customer to implement a knob so that they can override the AS path before they advertise it to you, yes, that's another option, but good luck with that. But that's surely a technical option. In reality, it may or may not fly. Asking your customer to change something, well, yeah. Yeah, so let's run through the control plane flow, how the hub and spoke really works. So we had two VRFs at the hub, PE, on your right-hand side, and the first VRF is called VRF hub out, and the other one is called hub in. Now spoke A advertises this prefix to PESA, or spoke A advertises via multiprotocol IBGP to PE hub. Well, it will actually advertise it to everybody by the virtue of MPLS VPN, right? And everybody else will look at their route target information, will match it. If they don't find anything matching, they'll discard it, except that PE hub will find it matching on the VRF hub out, because we configured route target import 1:1. If you flip back through your pages, you will see the configuration. So at this point, PE hub would accept these two prefixes, which are /24s, right? 171.68.1/24 and 171.68.2/24. PE hub would accept those two prefixes and put them in the VRF hub out routing table. Again, we'd also store the relevant label information in the CEF table. Then this prefix information will get advertised to the hub site. The hub site may send the specific routes back to the PE hub, or it may choose to send only the summary routes such as /16 back, right? As the case shown on the slide, it might just send a /16 back to the PE hub, and PE hub would accept that information within the VRF hub in, because it's tied to this blue interface, and would advertise that information via the relevant route target, because we have route target export to :2 configured within the VRF hub out. When that happens, every other PE spokes would accept that information within BGP and install that information within the relevant VRF routing table and advertise it to the spoke customer edge routers if there is a routing protocol configured. So that's how the control plane flow works, right? Our point to note here is that anything that's being advertised by PESA is not being received by PESB or vice versa in this topology. And that was one of the key requirements to do hub and spoke. They should not receive each other routes so that they don't receive each other's traffic directly, right, without involving the hub site. So the aggregate route is getting originated from the hub site towards the spoke site. Spokes are advertising the specific routes towards the hub site. We want spoke sites to get to each other via the hub site only, not by passing the hub site. That's the whole premise of hub and spoke. Was there a question at the back?
VRFs at the hub site?
The question is, do I need to do the VRFs at the hub site? Yes, because we need to implement hub and spoke. No, I mean, that's the only way, let me put it that way, that's the only way we can do hub and spoke. Now, I think if your question is, let me rephrase the question, do I really need to have two interfaces between PE hub and the hub site, hub CE router? You don't have to, but it's not the simplest way to achieve so, and that's what I had in the previous slide. If you just flip through the previous slide, you will see you can do this using one interface, but it's tricky, okay? And I have more information on the previous slide. But you must have two VRFs. That's something we cannot avoid. Yeah, we have to have two VRFs. And the bitches, I don't know if that creates any problem by any means. So let's look at the traffic flow for this hub and spoke. Now, what we saw in the previous case, spoke and spoke B advertised the routes to PE hub, and that got advertised to the hub site, hub CE router, and hub CE send the prefix back towards the PE, SA, and PSP, and so on and so forth. So now, host within spoke B is sending a packet to a destination that lives at the spoke A. PESB does the lookup in its VRF routing table and says, oh, I have the information, the VPN label is 35 and I have a label L1 to get to PE hub. PE hub is the router that advertised the VPN prefix, right, to get to this specific 172.168.11 prefix. PE hub basically untags the packet, sends that IP packet towards the hub site. Hub site would do an IP lookup as usual, and it will have more specific routing information, and it will say, oh, this 171.168.1.0/24 is reachable via this interface. So it will send it back to the PE router. Now PE router receives this packet on an interface which belongs to a different VRF, which is hub out. So now PE router does the lookup in the hub out VRF routing table, and then it says, oh, okay, well, this destination is reachable via PE spoke A. So PE hub encapsulates that IP packet back into an MPLS packet and sends that packet towards the PE spoke A, which will untag the packet and forward the IP packet to the spoke A. So that's how the traffic flow will work for hub and spoke. Now, let's expand on this. What would happen if you had multiple spoke routers connecting to the same PE router? If we put all those spoke routers in the same WRF at that PE spoke A router, then what would happen? All those spoke routers connecting to the same PE would be able to reach each other bypassing the hub. So it breaks hub and spoke. So one way that we used to solve, early on is by placing each of those spoke routers in a different WRF on the same PE router, right? That solves the problem, but the problem then it creates is the scalability issue. So now if I have, say, 200 spoke sites needing hub and spoke, however, they are in the same geographical region, which is very common if the customer is a bank customer, then I have to create 200 different WRFs on the same PE router. Now, this may not sound so bad, but let's think about this. What if they have these dial users, which may be in thousands? Right? These dial users come in, and what you are providing is a remote access to VPN. So you take dial users, put them in the relevant WRF, and each of these dial users should follow the hub and spoke. Well, in this case, you cannot afford to create 1,000 VRFs. It's just way too much. So to solve that problem, we created something called half duplex VRF. Concept is almost the same as we discussed before from the hub site perspective, in which we use two WRFs. We apply the same model in half duplex on the PE routers. But the beauty of this solution is we don't need two interfaces. We do that only with one interface, and we associate two WRFs with that interface. Okay? So it requires two WRFs, and just for the sake of understanding, we call one VRF as the upstream WRF, meaning it only takes the traffic from the customer edge router towards the provider edge router, and the downstream WRF, which will be the traffic coming from the MPLS backbone going from PE to the CE router, right? So two WRF, upstream for spoke towards hub and downstream for spoke from hub towards spoke. Currently, it's only applicable to virtual template because that's where it made more sense to put, and that's where we had the biggest requirement. But now it's being extended to normal interfaces as well. So let's quickly go through how this works. We would create on the PE spoke 2 different VRFs, and each of them will have either the export or the import route target, very similar to what we went through at the hub side. Okay, very similar, but the only difference here is that we associate both of these verbs to the same virtual interface, or the virtual template in this case. So what's going to happen is that the way this functionality is implemented, all the routes that are learned from the customer edge router, PE spoke, this PE router would install them in this downstream VRF. All the routes that are learned from PE hub or the remote PEs, this PE would install them in the upstream VRF. When the IP packet is sent from the spoke side towards either the hub site or any other spoke site, the packet will be looked up in the upstream VRF only. And as you would recall, upstream VRF routing table contains nothing but the routes received from the hub site. When the hub receives this traffic and sends it back to, say, the other PE router, this PE router would do the lookup in what kind of table? Fib or LFib? How many of you think it's going to be Fib when the traffic is received by the PE router from the PE hub? Fib? LFib? Okay, majority wins. No, I'm just kidding. No, it's the LFib. Remember, when the packet comes back, so this is something we went through in the tectorial yesterday. I don't know if some of you were in the tectorial. When the PE hub sends the traffic back to PE, it's going to be an MPLS packet. And PE router will always do the lookup in the LFib, which is the MPLS forwarding table, for an MPLS packet. PE router would do the lookup in the SEF table for IP packet, not for MPLS packet. Do not forget this. If anything you get out of this presentation is that FIB is used to forward IP packets and LFib is used to forward MPLS packets. So when the packet comes back from PE hub to PE spoke router, it's going to do a lookup in the LFib, which only contains MPLS to IP information. Boom, the packet is converted back into an IP packet, sent to the spoke site. We are all done. Question? The question is, will there be an issue if the hub site connected to a PE router which also connected to a spoke site? The answer is no, because you would place them in a different VRF altogether. The VRFs that gets used to connect the PE router to the hub site will be different from the VRF that we would use to connect the spoke site. So the question is, if there are 2 VRFs on the PE router, how will they get the routes to each other? Well, exactly the same way the extranet works. For extranet VPNs to work, we'll see that on the next slide, the router must have BGP configured. Doesn't mean it needs to have BGP session with the CE router as well. Okay? Do not forget that. This is more like a CCIE question if you're planning to take that service provider CCIE. Okay, so that's how the hub duplex works. How many of you today already do extranet VPN, by the way, in your MPLS VPN? Give me a few. How many of you have already heard of extranet VPNs? Well, still a few. So the concept of extra VPN, I mean, that's nothing new. What that really gives us is an ability to connect 2 different VPNs to each other. By definition of MPLS VPN, we say one VPN is private from another VPN, they cannot see each other, and so on and so forth. With extranet VPN, we kind of break away from that definition. Think about this practical application. You have a company A, it wants to open up part of its network to company B because company B is trying to act as a partner, right? A lot of us do that today. Or we recently merged with another company, or for sake of some time period, we want to treat them as an external company and only provide them access to our corporate and nowhere else, something along that line, right? So to do that, we need to provide extranet VPN. So if you're a provider, you will get your customer saying, hey, I have these 4 VPNs, could you have them some access to following destinations and whatnot. So extranet VPN is what that provides us the ability. How we do that? Again, by tweaking these import and export route targets. And I always suggest that use export map or import map. So here's the case study. Okay, it looks like someone is throwing all these arrows in my direction, but the case study here is that VPN A, the green color, has 2 sites, site 1 and site 2, and VPN A is trying to form an extranet with VPN B such that only site 1 can get to site B or vice versa, but VPN B site 1 cannot get to this site. This may be, say, financial site, whatever. So the way we would implement is by converting all these arrows into good-looking config. What we have here is that on PE1 we put export map so that we match only on 171.68/16 prefix. Okay, like in this route map here, we only match on address 1, which is 171.68, and we set the route target to be 3000:2, which is imported within VRF VPN B via an import map as well for extra precaution. You don't necessarily need to have import map here because we already got the route target import to 3000:2, which is what we are setting additionally on the 171.68/16. 171.68/16 will also have any other export route target that's configured within this configuration here. So this way, VPN B that belongs to this site will accept only 171.68A, 171.68/16 and advertise it to VPN B. In the reverse direction, VPN B VRF will advertise, look at the export map here, export VPN_B export, which has the route map. It's matching on address 2, which is 180.1.0.0, and it's tagging that with an additional route target 3000:1, which is what we are importing here. The point is 192.6 never gets tagged with the RT 3000:2, so it never shows up in this VRF VPN B. So that's how we implemented extranet VPN. In its simplicity, if you didn't want to deal with, say, import map, export map, and you just want to create a quick extranet, all you really need to do is put the right export route target and import route target on different VRFs belonging to different VPNs, and the routes will be imported accordingly. Right? So that's the simplest way, but I don't recommend that given the requirements you may have of segregating specific VPN prefixes only and allowing them to be imported at the extranet site. There was a question here. Also, I think what you're saying, they have an overlapping IP addresses, and you still want to do extranet VPN. How you do that? The answer is yes, you can do that, and I have another slide later on under the VRF AwareNet, and that talks about it. So if you don't mind, I would hold off to that question. Let's talk about internet access. So providing internet access service to your VPN customer is something not really new, but the way the market is spread out, if you look at the market, a lot of VPN customers seem to have their own ISP connection independent of which provider they go to for MPLS VPN, right? So if you are an MPLS VPN provider and if you are not in the ISP business and you want to get into that ISP business, you have to kind of offer this value add by saying you have only one circuit, you use the same circuit for VPNs, for internet, and for everything else. Even if you don't offer that by single circuit, just by assuming the responsibility of ISP, you surely get that customer retention. So internet access is one service that kind of becomes very important from the MPLS VPN service offering perspective. Just like it's true in this networking world, there's not always one way to solve any problem. So I wanted to put out 4 different models to provide internet to your MPLS VPN customer, and I have seen actually all 4 of them being utilized or being deployed in different customer networks already. So it depends what specific requirements here, it depends whether you like sun or moon. No. So 4 mechanisms are either you can use global keyword, and we'll talk about that later on, or we can use a different sub-interface, which is the simplest option, or you can do extranet with a VRF that has all the internet routes, or you could use VRF AwareNet. So the first one is about the global keyword, and I'll skip this slide because I'm going to get into the specifics. So here we are on the left hand side. I have the site 1 that requires internet access. It's already part of the MPLS VPN. On the internet is on the right hand side. So we have our ASBR router connecting to the internet. What we configure within the VRF, in addition to the usual VRF configuration of defining the VRF and associating that VRF with the PECE interface, we now configure a default route within that VRF with the global keyword, right? This is a fairly new knob if you have not seen this before. And this address 192.168.1.1 is the address of the next hop, which is nothing but the internet gateway, the ASBR. And this VRF default static route should be configured at every PE that has the VPN needing this internet access. In addition to that, we would also need the static route pointing to the site-specific route or the prefix at the PE router itself in the global table. Okay, so what we have done, we configured the global static route pointing to a VPN-specific prefix with the next hop of that serial interface. Okay, and now we have to redistribute the static route in BGP so that, well, of course, this is the internet model. So this route must be advertised to the internet. Whether and when it's done, that's an independent thing. But VPN site reachability must be provided to the internet. That's why we have this 171.68 prefix within the BGP at PE1, which will advertise it to the ASBR, which in turn will advertise it to the internet. The question is, if there is a routing protocol configured between CE1 and PE1, would that not take care of the advertising this specific route to rest of the internet, or do I really need a static route? The answer is, even if you have the routing protocol on PE-CE link, it's not going to help. Why? Because that interface is within the VRF. So the routing information that's learned from the CE is stored within the VRF instance. It's not in the global table. That's why we have the static route to put that prefix 171.68 in the global context, and then we redistribute that in BGP. So from the control plane perspective, Site 1 is sending a packet to the internet. The first thing it does, by the way, the packet is received not on the global interface, but on the VRF interface, right? So it's going to do a lookup in VRF routing and forwarding table, right? So if you look into the VRF routing table, it will say, oh, I got the default route, or the next hop is 192.168.1.1 with the global keyword. Because of the global keyword, then it's going to do a lookup in the global routing table. Now, here's an important point. It does the lookup in the global routing table not for the IP destination, but rather for the next hop. It finds the label, if there is one, it encapsulates the packet with the label value to get to the next hop, and then the packet is sent to the PE2 or the ASBR, and that packet gets received as an IP packet, and assuming that ASBR has all the default route towards the internet, the packet will be sent to the internet. Now the response comes back with the 171.68.00 IP address. That IP packet would be received on a global interface, not on a VRF interface, right? On this router PE2 ASBR here. So it is going to do a lookup in the global routing forwarding table. So it looks up and says, oh, it's available via 192.168.1.2 because PE1 had advertised this information in the regular BGP IPv4. So it does the lookup in the global routing table, it has it, it forwards the packet using the label value to get to that next hop, which is PE1. PE1 gets that packet as what kind of packet in this case? IP or MPLS? Okay, I'm sorry, nobody raised hands. So MPLS, how many of you think MPLS? How many of you think IP? And how many of you think those who didn't raise hand in either case? Well, it's binary, my friends, it's binary, 0 or 1. It is either this or that. There's nothing in between. Okay, so the answer is it's an IP packet. It's not an MPLS packet. Why? Because this packet is being sent in the global domain. This 171.68.00 is in the global table. So when the packet gets to PE1, the label of that packet 30 was already powered by the PHP router. That's why when that packet gets into PE1, it's an IP packet, and it must do an IP lookup in the CEF table within the global table. And it should be okay because we had put the static route before, right? So it will do the lookup here and send the IP packet towards the customer edge router. So that's how this works. The pros, well, you could have multiple internet gateways per VRF, and you can segregate internet traffic going from one VPN site this way because you have that ability in that static route. So there's a flexibility on that side. Well, of course, the disadvantage is you have to do that statically, and it kind of takes away any other default route's presence in that VRF. This may or may not be suitable to a lot of customers. There was a question here on this side. The question is, should the internet gateway participate in the private VPN? Well, the answer is no. And when I say participate, when I think of participation, I would think that the PE, the gateway router, should be defined with the VRF, and it doesn't have to. It's the same old ASBR, just with the internet routes. It receives a bunch of routes, it does a lookup based on routes, and that's it. There's no VRF on that ASBR. Oh, so the question is, why should the packet coming back from internet, and when it hits PE2, why should that packet not be sent as an IP packet to PE1? And why should it be sent as an MPLS packet? or vice versa. Why should it be? Okay, so let's think about it. What happens if in my CEF table, and this is MPLS 101, has nothing to do with VPNs, but I'll still answer. What happens if a packet hits a CEF table and if there's a label available for that prefix? Will the packet be sent out as an IP packet or MPLS packet? MPLS. And this is exactly what's happening here. PE2 has a label to get to PE1. Okay, it might have used LDP or RSVP, we don't know, but there is a label available. And if there wasn't a label available, it will send out as an IP packet by all means. And of course, the packet will likely get dropped in the core if there was no MPLS or if the specific VPN routing information was not available on the core routers, which would be the case typically. Now, in this case, there was a label from PE2 to PE1 to get to PE1, and this route 171.68.00.16 is advertised by PE1 as a normal BGP IP v4 route to PE2. So what PE2 has as a recursive route, it says, oh, 171.68.00 is reachable via PE1 and I have a label to get to PE1. It just does the recursive resolution, puts the label within that 171.68.00's entry against the CEF. It's the same thing. No, you're right that it will utilize the global routing and forwarding table, but we have MPLS for global routes as well, right? MPLS is not used only for VPNs. It's a normal thing. Yeah, that's it. There was another question somewhere here. Yes, sir. You could say that, but in general, the concept of PHP is when the router gets a label packet and it does an LFIB lookup, and if the outgoing label says pop, it's going to pop that label out of the packet. If the label stack had only one label, then it's going to convert the packet back into an IP packet. If the label stack had more than one label, then it will just remove the topmost label, leave rest of the label stack intact, and send out that MPLS packet. Okay, so the next one is the separate PEC subinterface. Question. The question is, for this option to work, do I have to use public addresses in my backbone as well as in my VPN sites? The answer is, you don't have to use public addressing within your backbone. However, the address that gets advertised to the internet must be a public address. So that's why I said in my earlier explanation, where does the NAT take place is kind of independent of the discussion to understand this model. So let's think about it, right? How do we address this backbone? I could use public addresses or I could use private IP addresses to address the WAN interfaces. And if it's the private IP addresses, when the trace route is done, it will use its interface IP address and encode that and send it back in the trace route response. Now, of course, if you're using private IP addresses, you may just hide your whole backbone and show it as a one hop. Yeah, you can always use unnumbered, of course. But the VPN site should use public IP address if it needs to get to the internet. I think that's kind of 101 thing. I'm not sure. This is an MPLS VPN topic, not RSVP. So let's move on. So subinterface model is the very simple model in which we are creating another subinterface or another logical or physical interface, and that's how we would do it here. So one interface is plain old VRF, the other interface is within the global table, and this gives us an ability from the PE perspective to send full or partial internet routes to the CE router. So this option would be more suitable for the customers that want to have partial or full internet routing table, right? Because if you put them within the same VPN context, it's a lot difficult to do that. With this model, you can simply advertise all the partial or full internet routes over this global interface or global BGP session that you would have to establish between PE and CE using this global interface. This also means the PE router would have to carry the internet routes, right? You could do that via some tricks by having multi-hop session between CE and ASPR and having PE routers carry the default route in the IGP, but that's just a trick, something I would not recommend. So that's simple enough. From the key here to understand is that CE router is the one that has to make the determination about whether it sends the traffic on the VRF interface or on the global interface from PE perspective, so that the traffic gets handled correctly, whether it's going to VRF or the VPNs. So the advantage here is, of course, that the separation is performed at the CE router itself, whether the traffic is going to the internet or to the VPN. And you can also do some kind of dual homing concept here as well. disadvantage here is that CE router, we would have to be careful with the CE router because there could be a looping scenario. If the internet route is learned or this interface, and then if it's advertised back, then we will end up hosting the PE router altogether. So be careful with that. The third model is the extranet with internet WRF. In this model, all we are doing is really putting all the internet routes in one WRF and then having all the customers that need internet access do the extranetting with that internet WRF. That's it. But watch out, because you're kind of replicating those internet routes in multiple VRF tables. So this may be okay for one customer, but if you have to do with multiple customers, you may end up burning the whole PE router's resources. Yes, sir, question? Question is there any split tunnel kind of scenario here in which the traffic to the internet is sent to the internet on one side, and no, there's nothing like that here in MPLS VPN. It's as simple as one interface going this way. That was the previous scenario. In this scenario, it's just extranetting with the internet WRF. Then the fourth model to do internet access is by using VRF aware NAT. Okay, and we'll discuss VRF aware NAT separately in the next section. So let's move on. The fifth service is the VRF selection. I don't know how many of you have heard VRF select service. So far, all we learned was that a VRF must be associated to an interface. There has to be one-to-one relationship, period. With VRF select, we break that notion to some degree, because now if I wanted to associate multiple VRFs to the same interface, I can do that. The advantage here is that I use some other classification mechanism such as source, destination, IP address and whatnot in layer 3 or layer 4 headers to classify the packet and then map it to the right WRF and then do the lookup on the packet in the relevant VRF routing table once it has been mapped to the right WRF. So let's understand where would it be more applicable. Right, so we have this rule, right, at least in US, the open access, in which if I'm a subscriber and I get my service from, say, Time Warner, and I want to get my cable service, but I want to choose my internet access from another ISP, right? And with that, cable company, the Time Warner, has to do some magic so that they can offer me the option to go to AT&T as the ISP or any other ISP that I want. So the way they would do so is by utilizing this VRF select abilities. So if there are 3 different VPNs, I'll call them just the ISPs, right? 3 different ISPs. And here's the cable, HFC, whatnot. And here's the cable CE1 that comes and connects to the PE1. And it's a global interface. Why it needs to be in the global interface? Because this cable company may also be an ISP, and it would also need to send the traffic to the internet for its own internet subscribers, and it might be coming well on the same interface. The way this works is on the interface serial 0/0. This is a global interface, by the way. We create a policy, we define the route map, and we associate more than one VRF with that interface. And in that policy, in the route map, we define the classification criteria and we map the relevant WRF to that specific criteria. So in this case, if we know based upon the source IP address, that's one way to do it, and that's what I'm showing on the slide. If you use the source IP address to map the packet coming from this source into the relevant WRF, all you need is you define an access list for that source address and you set the relevant VRF. So any packet coming from this host will be mapped to the Brown VRF routing table, and then the packet will be looked up in the VRF Brown routing table, and then it will go to the VPN Brown site, wherever that is. So you can do the same thing for other VPNs as well. So there's one applicability. You can do this in any other scenario as well, in which you need to have more than one VRF associated with the same interface. This is how you would do it. And this is called VRF select. That's another name if you do a lookup in CCO. Question? Yeah, so the question is, if it was a one-to-one mapping, then I could just show, VRF blah, and it will give me which interface it's associated with. Well, this would still work. If we do show VRF blah, it will tell you that VRF green is associated with serial 0/0 via VRF select, not the traditional way. So remote access VPN is another service that you could offer, and when we say remote access, it's really either you could use IPsec or some kind of dial-in users, and you could terminate them into a PE and map into a relevant VRF. There's a whole new session, completely dedicated session, networkers about remote access to VPN. So here I want to just introduce the concept and for you to, pick up on those other topics if needed be. So the way that would work, you could have your remote users coming somewhere from in the internet. They would get to the PE router, which would terminate either the IPsec session, as shown on this slide, or the dial PPP session. So we could also take PPP sessions and terminate them directly into the VRF. So all these sessions go and get terminated within the VRF, and at that point, it's just plain out MPLS VPN. So it does an IP lookup in the VRF routing table, and then from there, it just goes to whichever the site's supposed to be going. So the key here is that the feature that you would need to worry about or need to keep in mind is the mapping of the PPP sessions into the right VRF, or mapping of the IK session for IPsec into the right VRF. So VRF aware NAT. So as we know that VPN sites are likely to use overlapping addresses if they're using 10/8, for example, and if we need to implement say extranet was asked before, or if we need to provide internet access for those VPN customers that use private IP addresses, then sure enough, they need some kind of netting functionality. In a lot of cases, VPN customers may choose to do the netting functionality within the customer premise itself. Now we have the feature VRF aware NAT. So what you could say that, hey, you don't need to do netting at your own place. I would do the netting for you, either at the local PE or at the remote PE. So let's see how this works. Well, of course, the netting from typical perspective, you would connect the inside interfaces with the private address space, or the public side with the global address space. You could do it other way around as well. The point that we always have to remember, NAT 101, that NAT occurs after routing for traffic from inside to outside interface, and vice versa for the other direction. The key here is that each NAT entry is now associated with the VRF. Right? This never existed before. So now each NAT entry has the VRF awareness, and it all works for either IP to IP, IP to MPLS, MPLS to IP. So let's see how that really works in this pictorial format. So you have IPNet Insight configured on this PE-ASBR. This is one deployment model. You could very well put the NAT functionality right on this PE, and by putting the NAT inside on the VRF interface and NAT outside on the global uplink, it works fine. In this case, I'm showing a one deployment model. So you have IPNet inside on this MPLS interface, and then IP outside on the interface facing the internet, the typical model that you would always see. Then you would need to have some VRF specific config that we all have to do anyway, independent of VRF aware NAT, and then something VRF aware NAT specific. So from the VRF specific config on this PE-ASBR router, by the way, this is what we would configure. Even though this ASBR may not have any customer connections, we would still need to configure the VRFs. Those VRFs that need internet access. So say in this case, green and blue, which looks like blue and yellow in the config. Now configured as usual, right? Both import, export, route, target. In addition to that, we also advertise a default route from this PE-ASBR within each of the VRFs towards the relevant PE routers, right? To attract all the internet traffic towards the PE-ASBR from these sites. And then we define the address pool, like in case of NAT we would have to do. We create the NAT itself by associating that pool with the VRF and by the source list, which is defined later on. So what we are saying, that anything that comes from 10.1.1.0 as a source IP address, translate that to the address defined in this pool green, which is /24, and this should be handled in the green VRF. And we do the same thing for blue as well, which looks like yellow. But note here that we also configure these two default VRF static routes with a global keyword like we learned before. Okay, but that's all we need, so that any traffic coming in the VPN context here will be forwarded using the default route towards the internet. I don't know if you noticed, both of these sites are using the same IP address. It's overlapping. So note, I'm using the same access list to classify the source addresses. I could have used another access list, but there wasn't any need. And then I'm mapping that to different pool and different VRF. So that's the key. So how it works in the forwarding plane. So the green site sends a packet to the internet. Okay, source 10111 going to the internet someplace. It gets received at the PESBR as what kind of packet? MPLS packet. So it will do a lookup in what kind of table? LFIB, thank you. And when it does the lookup in the LFIB, it will untag the packet. And now it gets an IP packet. On this IP packet, it will perform the NAT functionality, right? Because there's a feature configured on the outgoing interface. And when it does the NATing, it creates this NAT entry according to the VRF on which it was received. If you don't remember, within the LFIB, we do store the information for that this label is associated with this VRF. Okay, so that's how we know, even though we received an MPLS packet, we know what VRF it belonged to. So that's how we glean that information. So we create this NAT entry. We also associate the VRF ID. This is something we didn't have to do for typical NAT functionality, but this is how the VRF aware NAT works. And then the packet is forwarded to the internet with the changed source IP address. When the packet comes back from the internet going back to 10.1.1.1, then first the NATing takes place, right? So the destination would be 24.1.1.1. The NATing will take place so that the destination IP address will get changed to 10.1.1.1 from 24.1.1.1. And then it will say, the VRF table that I have to do the lookup now is the green VRF routing table. So after the NATing gets done, it will do the lookup in the green routing table and forward the packet towards the CE2 router. Same thing takes place for the VRF blue as well for another site, and the internet or just the whole VRF aware NAT works fine whether there's overlapping or there's no overlapping. So although I showed the overlapping example, it doesn't have to be overlapping and it works fine as well. Quality of service, right? All of us care for costs. The good thing here is that cost mechanisms don't quite change when we introduce the MPLS VPN concept. The same old cost mechanisms of doing MQC, you classify, you police, everything is still applicable, whether it's a precedence value or DHCP value or an EXP value. EXP value is what we use within the MPLS. I'm sure you guys all know this. And by default, IP precedence bits are copied into MPLS experimental bits. That means if you use all the DHCP based model, I am sorry, you cannot use all the 6 bits when MPLS kicks in. You can only use 3 bits. That's why I said precedence bits. Right? So if you use DHCP, then only the first 3 most significant bits are copied into EXP. So you just have to watch out for that. Everything else just works the same, almost. I mean, there are always platform-specific dependencies, which is common for any cost. MPLS VPN is no exception. But from the concept perspective, from the configuration perspective, it doesn't change. Okay. Multicast service. I know some of you talked about it. Multicast VPN today is available. It uses GRE-based transport. Why? Because MPLS multicast has not been available yet. I mean, it was the last year is when finally IETF, Cisco proposed a model to do MPLS multicast for multicast VPN, and I was one of the contributors to that draft as well. So we can now do multicast VPN using something called MLDP, right? It's multicast LDP, meaning you have more extensions within LDP to use to build multicast tree. You don't have to have PIM now. You can use the same existing LDP to build multicast tree. It's in beta, so if any of you are interested, let me know. We can get you an EFT code. Point-to-multipoint TE is also available again in beta. Nothing actually in production yet. But today, the way multicast VPN is deployed by using GRE encapsulated. So there's no MPLS. We have just multicast packet encapsulated inside another GRE packet, which actually uses multicast addresses within the backbone itself. There's a whole new session, well, not new, but there's one session, Advanced IP Multicast, that talks about this whole thing in detail. So I'm not going to go through it in detail here. But if you have any questions specifically, come see me after the session. so far we all said that MPLS VPN requires MPLS backbone. And here comes the service in which we say, well, it's not really service, but it's more of a different paradigm by which you can provide VPN services, same RFC 2547 services, using plain old IP transport. Nothing else needed in the core. How many of you would like to have this? Why? Because it's there? It simplifies it? Okay. Well, IP has its own challenges, MPL has its own challenges, so you're not going to run away, by the way. Very good question. So what would you do for multicast here then? Right. So for multicast, remember today's multicast implementation, whether independent of vendor, utilizes GRE. So it utilizes GRE as an outer header to hide the VPN specific information in the packet, right? So it uses another header. So that's the same concept we use here in the IP VPN as well. What we do is that instead of using an outer label to get to the next hop, we use an header, and either a GRE header or L2TP header, some kind of IP header. But note that we still allocate MPLS labels to get to the VPN prefix. So you still have MPBGP, you still do the multi-protocol BGP to allocate labels for VPN and distribute labels to every PE router. It's just that there's no MPLS in the backbone anymore. So from the packet perspective, that's how it looks. You have your VPN v4 packet information here, then you have VPN v4 IP information, the IP header 20 bytes, then the label for that prefix, then you have L2TP v3 header, right, the session ID and cookie. You could also use GRE. The only thing changes is again, GRE header and the transport header, and that's it. When the PE router receives the packet from the customer edge router, it converts that packet into an MPLS packet as usual by appending this VPN label. Then it puts the IP header, right, to get to the next hop right here. So that IP header would say, I am the source, being the ingress PE router, and here's my egress PE router's address as the destination IP address. All the routers in between just do the IP lookup and forward the IP packet to that egress router by the virtue of IP forwarding. When this egress router receives that packet, it de-encapsulates that packet, remove the IP header, and then puts the packet as an MPLS packet back into the MPLS path, and then from there it's just an LFIB lookup and IP packet back out. So that's the IP VPN. How many of you have heard of multi-VRF CE or VRF Lite? This is one of the most attractive features that I've ever seen gaining traction in the last 5 years, I have to say, especially within enterprises. If you guys want to do virtualization, segmentation, you can do that by utilizing the similar VRF model. Remember earlier in the presentation we discussed, what does VRF provide? It actually creates virtual routing instances within the same router. So I can have multiple virtual routing tables. That's what we exploit here. There's no MPLS, no LDP, nothing. You don't need BGP either. So as long as we create multiple routing, VRF routing table, and then we associate those multiple interfaces with multiple VRFs. So you have VRF coming in, VRF going out, plain IP. VRF1 here, VRF1 out, VRF2, VRF2 out. So you put them in different interfaces and that's it. So that's very attractive. So here's one application, one applicability of multi-VRF. And this is more actually relevant to the MPLS VPN providers, this specific model. I got my MPLS VPN network, I have my VRFs configured at the PE. This is where we typically stop from the provider perspective. We have one interface going to the customer site and that's it. Now what we have done, we instead of having one interface, we have multiple interfaces between PE and CE. They could be either logical interfaces or physical interfaces, some distinction there. Now the CE router is also configured with VRFs. So you have say Ethernet 00 and Ethernet 10, Ethernet 20, and this could be say frame relay. So I create multiple DELCs here and associate DELC 100 with the same green VRF which goes into VRF green here as well, and from there it's same old MPLS VPN. So what we have done on the CE router, we have created multiple VRF routing tables to segregate the traffic right at the CE. So now this could be going to multiple buildings or multiple floors on the building, and I can extend that same virtualization that I could have done using layer 2 switch just by putting one router and having everything layer 3.